Ben McMorran on interactive measurements in electron microscope.
Thank you for the introduction and thanks for the invitation. This is really quite amazing for me to meet all of you in person. I've been reading all your papers for quite some time, and it's a privilege for me. And thank you also for all the terrific ideas. So today I'm going to talk about our work with interaction-free, which I put in quotes just to appease everyone, measurements with electrons and an electron microscope. So the data that I'm showing here is the output in multiple ports from an electron Mach-Zehnder interferometer. So I'll discuss how we did those experiments. First, I wanted to acknowledge the people that actually did the real work. In particular, Amy Turner, who now has her PhD, and Cameron Johnson, same, primary contributors to this, very talented grad students. And we collaborated with Peter Pruitt at TU Delft. And in particular, we benefited from a lot of conversations with so many people. Really, I could take up 4 slides with just a list of names. But Mark Kazovich had visited us a while ago, and we were talking about interaction-free measurements. We happened to have an electron interferometer at the time, and I was convinced that maybe we should go ahead and try the simpler interaction-free technique, meaning one single pass-through. Could we do anything useful? Not multi-pass, but single pass. Okay. So first of all, I'm going to give some background. So you're not electron microscopists, so I'll talk about some of the major features of these instruments, as well as sort of the holography and interferometry work that we've done. I'll spend a little bit of time talking about the actual setup and how we did this, and then of course the interaction-free measurements, and then if there's time, where we go beyond that. So inelastic scatter. Here's a quite complex image of a TEM on the left. It looks like a microscope, except it's a little bit taller. And the optical microscopes that you might be used to from like the 6th grade, the light comes from the bottom, let's say. Here, the illumination comes from the top. But other than that, it works very similar to a microscope that you might have in the lab. It uses electrons. We have a sequence of lenses, a stack of lenses with magnetic fields. So with a twist of a knob, we can change the focal length of those lenses. And then there's spectrometers and things like that. So here's a complicated diagram. Don't look at it too much. It just has a lot of parts. I'm trying to impress upon you that it has a lot of parts, but we can tune those parts. One of the interesting things of modern microscopes, there's been some quite amazing engineering going into these systems, is they're almost a laser-like point source of electrons. So they're quasi-monochromatic. So you can get a tenth, down to a tenth of an EV, electron volt, energy spread on a 300 keV beam. And if you calculate it out, so the de Broglie wavelength is quite short, we're talking 2 picometer wavelengths, 300 keV. The coherence length, due to the energy spread, is just a micron or 2. So that's quite short compared to a laser that you might have in the lab. However, if you take the ratio of the coherence length, how many wavelengths fit in a wave packet, it's large. In fact, it's similar to a heating tube. That's in the longitudinal direction, also in the transverse direction. So these are emitted from a point source through a quantum process. So a field emission source is a very sharp tip, and the electrons tunnel out. And in fact, it's similar to some of the effects we're talking about. Somehow, in order to tunnel out, the electrons have to be able to see their reflection in the surface. And how do they know that they can see their reflection without already being outside of the tip? Just that kind of routine process, kind of interesting. Well, it's emitted from about a point source, and you can collimate that, and you can spread the beam with a lens. And using apertures, you can get a very cold beam in the transverse direction, meaning the electron has phase coherence across the width. You can vary the width from an angstrom. You can focus these beams down to really sub-angstrom widths. And scale it, or you can spread it out over millimeters or centimeters. You can vary the current from picoamps to nanoamps. That's millions to billions of electrons per second. However, one difference is that they're non-interacting. So unlike photons, there's no phase coherence from one electron to the next, or even in their rival frames. So there's maybe been some very rare, if you integrate over days, some possible findings of anti-bunching due to Fermi Dirac statistics. But these beams are pretty sparse, so mostly non-interactive. The experiments that I'll show you, you can think of as single electron experiments done millions of times. There's many different kinds of lenses. So you can have round lenses. Again, you can tune those. There's aberration correctors. There's cylindrical lenses that you can tune. There's a spectrometer. So it's a bending magnet. We'll spend a little bit of time talking about that. And now single electron sensitive detectors, both imaging detectors and bucket detectors. Okay, so now I want to provide a vision. So here's a reconstruction of the trimer of the spike protein. That was the little key that would get into our cells of this variant of coronavirus, COVID-19, or SARS-CoV-2. And this was actually not, it's an image, but it's an image formed by tens of thousands of these particles. So one vision for the interaction-free measurement is, can we apply it to image these things better, so molecules instead of bombs? So I found this was the paper that came out in January of 2020. So this study, it isolated these proteins within several days of finding SARS-CoV-2. And then it found an image and it reconstructed that image after 13 days, I think. And then it was one of the quickest publications in the history of science magazine. Okay, so how do they take these images? So you're looking at a raw image of a bunch of these. If you squint, maybe you can see these kind of gray looking blurs. And if you were to zoom in, if you were to kind of reverse pinch to zoom, you wouldn't see much else. It's just kind of a gray blob.
What frequency was that oscillation actually at?
Oh, good question. I don't know.
Is it faster than it was shown?
Yes, so they do not catch them actually moving. They'll catch them in different morphologies, but they can't see this moving. So these are embedded in a vitreous ice. So very thin film of water ice. You flash freeze it so it doesn't crystallize. So it's amorphous. And they're flash frozen at all these different angles. And they're very, very blurry. But we use computer algorithms to reconstruct the average structure of these things from all of these very, very blurry images. So here's some maybe best raw images that you can get of the whole coronavirus. So pretty low contrast. You certainly, at least in my eyes, you can see atoms, although that's what ultimately you'd want to do, is where are those carbon sheets? Where's the nitrogen atom? And actually, these things are completely clear. So these are in or out of focus images. If you had an in focus TEM image with your maximum resolution, you would see basically nothing. It'd be completely grayscale. These are very, very electron transparent. So the only way to image these is to purposely defocus and change them to that phase ripple that the coronavirus is introducing into a measurable intensity ripple. Okay. Here's another rough image. Here's some parameters from that paper. So this tells you, let's see, magnification, pixel size terms per exposure somewhere. It tells you how many of the particles extracted. So the automated imaging system, you have to take thousands and thousands of these images across the sample. And within those images, the software will help you find 631,032,000 individual particles. And then it will form this structure from it. Okay, so I don't do this. I'm not a cryo electron microscopist. We'll talk a little bit about what's under these things. So you have to hold this in vitreous ice for one thing. So you have to keep it cold. You're now imaging these very delicate objects. So a biomolecule is made of carbon and nitrogen and oxygen. And the one thing that those things, I'm not a chemist, but if I look on the periodic table, I know that it's pretty high up. So that means they're very light, they're lightweight, which means if you exchange momentum between an electron and one of those atoms, you can shift it a lot more. You can shift those atoms around. And right now, the limitation is using this technique, you can only image structures that are maybe down to 10 kilodaltons. So that's 10 to the 4 atomic mass units. So that's the number of neutrons or protons you have to image. And you can't go any lighter. So you couldn't hope to see things like ammonia or even DNA, like Mach-Zehnder there. And right now, the limiting resolution depends on who you ask. It's about 2 angstroms. Some people will claim a little bit less. So it's getting near atomic resolution, but there's lots of important things that you want to see that you just can't right now. Okay, so there's been a lot of papers on what the fundamental limits are. And one of them is you're essentially exchanging momentum with the sample in order to image it. And when you do that, you can shift the atoms. What's more is that the atom or the electrons pass through the ice. They ionize the ice and charge it, and the shifting of the water molecules. You're not even melting these things, but you can imagine these invisible chains of water molecules will move, and that will cause your little protein chains to move around. And so the rule of thumb is if you get about 10 to 20 electrons per square angstrom in your image before you start to damage or alter your sample irreversibly. So about 10 electrons per atom. Okay. So that's a vision. I'm not going to say I'm going to tackle that, but that's one thing that we could do that would certainly be knowable, is to apply interaction-free measurements to see if we could image a molecule, a biomolecule, without damage here. So that's a vision that Mark Katzevich shared with us earlier. Okay, so shifting gears, a new technology that a bunch of different groups have developed is the ability to coherently manipulate free electrons. So both in time and in space, you sculpt the electron phase and the momentum, which is a new word, I just see that. Okay, so as an example, there's these vortex beams, these free electrons that can carry orbital angular momentum. That's just one of kind of an arbitrary example. There's many others. It's one kind of simplistic technology to do this is you could use a hologram, a diffraction hologram. So we do this with using a piece of glass. So we don't have a spatial light modulator for electrons. We have glass, essentially. And inside this little silicon wafer, it's like 3 millimeters across, not 30, not 300. It's 3 millimeters across. And within that silicon wafer, there's a square window. And that glass pane in that square window is silicon nitride. And so what we do is we mill grooves, a pattern, into that silicon nitride. And it's so thin, this is a commercial product that's used as a microscope slide for a TEM. So it holds your sample, the electrons pass right through it, it's transparent. And all we're going to do is sort of shift the electron waves as they transit through to coherently print the phase. There's all kinds of things you can do with that. There's gratings with a fork diffraction dislocation, and you can produce these electron vortex beams that carry this quantized orbital momentum, or other arbitrary modes, or mean Gaussian modes, superpositions thereof. You can reconstruct phase after producing these phase, so it's a focal series of electrons, electron beams that have this interesting three-dimensional structure in free space. You can do kooky things like twist the electron beam up. And so this is a three-dimensional reconstruction of the actual shape of the electron beam. So the electrons are winding down the column in free space. They're not orbiting any kind of magnetic field. But it's okay. The electrons in superposition in these two places so that the center of mass isn't accelerating, the center of charge isn't accelerating. Okay. So all these crazy things we can do. We can remove aberrations so that the lenses of the microscope are like a spherical lens. So just like on a droplet of water, you can see an image if you look through it, but that image starts to get distorted off to the side. The same thing is true for a magnetic lens. You have to remove the aberrations. We can do that holographically. And all of these things can fit on a single window within this little chip. We put that into an aperture. It's a nice technology. Okay, what I'm going to talk about here specifically is just using straight gratings. So not so much a hologram, it's a phase grating, which I guess is just one of the simplest holograms you can imagine. But what we've done is we've engineered the phase corrugation to maximize diffraction efficiency in a way that we want. So for example, we can get a phase depth, modulate the depth of the grooves to make a beam splitter. So one electron beam goes in, it's the direct image of the electron beam. As we put this grating in, we can divide that into two and suppress at 0 diffraction order. So every electron entering this grating gets diffracted into a +1 and -1 order, and that's going to be our beam splitter. Now, that said, these are fairly transparent, but they're not absolutely transparent. We actually do scatter electrons inside the membrane, and those typically hit the liner of the microscope, but it does remove them, and that will become a problem for us later on. Okay. Well, we put this grating in our microscope. When we take a picture, we want to see if we made the right thing. The spacing of these grooves is as small as we can make it. We've made them down to 40 nanometer spacing. Typically 100 or sometimes 200 nanometers is what we'll do. Those diffraction angles are still quite small. So 2 picometers is our wavelength, and our diffraction grating spacing is on the order of 10 to the -7 meters. So our diffraction angles are micro radians, so very small. However, that's what the transmission electron microscope is designed for. Every microscope, every telescope is designed to make small angles big. So we can take a small diffraction angle and still resolve diffraction. Okay, well, here's an image of our grating. Zoom in, here's grating bars. Now, I'll submit that whenever you have an imaging system that's looking at a periodic object, you've made an interferometer. So the spatial illumination is now modulated. You've created diffraction orders at some intermediate plane, and then your imaging lens is taking those different Fourier components and overlapping them to interfere to form the image. So if we turn down our microscope and we expose it a single electron sensitive detector that can run very fast, then each of these little spots here is a 1 or maybe 2 electrons in a pixel. If we let that run, there's this classic experiment where we see the smattering of electrons. It had just started to, it's like the beginning of a rainstorm here. At the beginning, so they got these raindrops hitting a dry sidewalk. Seems to be like rain, nothing special, but if we let as the storm continues, those droplets now appear to hit in only particular areas. And so it's one of the magic things about quantum mechanics. Okay, now even when we only have a few electrons hitting our detector, there's still information there. So we can take a Fourier transform And we see that in these particular areas, there's these persistent Fourier peaks. So there is some periodicity in even this kind of noisy image. Okay, so that's a direct image of interference fringes. We heard the talk. Andrew told us how we could maybe use those interference fringes directly to do IFM. So we could look in the trough of one of these interference fringes and ask, do we ever get an electron there? And if we do, that means one of these Fourier peaks must have been interrupted. But since our stated goal is maybe to image this or to apply this to image biomolecules, we need to make this fairly efficient. So for that, we need a Mach-Zehnder interferometer. Okay, so for that, we'll use two gratings. Here's a schematic of the setup. So it's just a 4F imaging system, or 8F, depending on what you're looking. So here we put this blue thing here is the grating. We've illuminated it from the top with a coherent electron beam. That will produce two diffracted beams. We'll have a sample plane here. This will eventually become our shutter that we're using to aperture off one of these panels. And then instead of mirrors, we're using the imaging system. So the imaging system will defocus and recombine those different paths such that they interfere, and we put a second grating beam splitter at that interference fringe. And now we get discrete outputs. So electrons in this path have come both from this one and gotten diffracted this way, and then also come from this path and transplanted straight through to interfere likewise over here. And then we'll use a detector that's just a multi-pixel imaging system with high quantum efficiency, with forms of Mach-Zehnder and forms of discrete outputs. Here's another more complicated system. There's actually a lot of different lenses in here. So there's projector lenses, there's 3 condenser lenses, and the grad students are impressed because they don't know how to hack those. It's like trying to do interferometry with a Canon. Is that a Canon or a Nikon? Where they purposely design these things to be a push button thing, and that's kind of how this is designed to be. So you have to hack it to be able to access these microscope parameters. Okay, so what we can do is we can introduce a path length difference just by shifting one of the beam splitters. So here's us shifting the second gradient beam splitter and looking at the various outputs. You'll see that we don't just get 2. We don't just get 2 equal intensity outputs. We get something more complicated. However, if we call this a bright port, then we can see that when it's bright, there's another port that's dark. We've done this in multiple ways. We can use blaze gratings to get interference between the 0 and +1 diffraction orders. So we can tune this asymmetry a bit. Okay, so our one grating beam splitter isn't perfect. That's another stipulation. We're not just producing 2 beams, we're actually producing other higher orders too. We filter some of those out, but that's an A for us. And then likewise, our output grating is supposed to be symmetric and identical to the first one, sometimes it's not, but it also produces higher diffraction orders. Okay, so that's a Mach-Zehnder interferometer. Now let's see, how do we do this? Okay, so as Mark Katzovich mentioned, Paul and him had kind of envisioned how to expand this using multiple measurements, multiple weak measurements. And subsequently, this is applied to imaging, various other papers. There's a neutron interaction-free measurements with neutrons, where they're presumably actually trying to implement quantum bomb detection. So I can imagine a shipping container with a very sensitive nuke in it. Maybe they're, sounds to me like they're just trying to get funding so they could do a cool quantum experiment. Okay. That's easy. Then there's these proposals for applying to electrons. So in one envisioned system, you have sort of a cyclotron system with a beam splitter. You have to prepare the electron in some kind of position. of these electrons circulating, and you'll have some kind of measurement in one of those paths. And then Peter Pruitt and Mark Kasevich and a lot of others got into this, formed this vision of a quantum electron microscope, where they would apply multi-pass imaging to make this a more efficient technique. Of course, if you have a 50-50 beam splitter, you can only hope to get an IFM click about 1 out of 4 times. And then we apply the same thing to electrons using the system. Okay. So we don't need to show this. So the 50-50 beam splitter, of course, we've got this chance of lucking out 25% of the time without blowing up a bomb. The question is, if that is an atom, we're not so concerned about blowing up the lab, we're concerned about altering the protein that we're trying to image before we have a chance to get sufficient contrast. And so if we can reduce the dose of electrons required to image that, or to determine whether there's an atom there or not, that can still be sufficient. It can still be a sizable effect. Okay. Now, if we use a weak probe beam, I'm trying to use a darker gray for the reference path and a light gray, a weak beam in this other interferometer. You can still tune it so you get all of your output into a bright port. And now, the probability of bright port detection or dark port detection is becoming equal to the probability of the probe beam hitting your sample. And so, in that limit, with just a single pass, you get up to a 50% efficiency, assuming that every time you get a bright port click, you just rerun the experiment. So the idea is that you expose, you place your probe beam in an electron microscope on a new pixel of your scan, and you just wait until you get a dark port click, or you let the normal bright field, bright port signal form your normal image. That's the idea. Okay, inside the electron microscope, here's the experiment we did. So we're going to use an aperture, a knife-edge aperture, it's opaque, it's a flat aperture, as our shutter. Okay, we've got these gratings on the initial and output of the interferometer, and there's our interaction plane. Okay, so I'll show the results here. The initial results. Okay, so if we move that second grating back and forth, so have nothing in it, we're not blocking any of the fields, the shutter is out. This is the kind of output that we would see. So as a function of the path length difference of the interferometer, that's the vertical axis. This is the real space image of the outputs. So again, we're not seeing just 2 outputs, we're seeing a bunch of different outputs. But you can see that they oscillate as they should. And we'll call this the dark port. So if we shift the grading such that we're sitting right here, then that means this dark port should never click, or very rarely will click. And then a bright port would be over here, or one of those other interaction orders. If I turn around on the side, I'm showing on the bottom, actually, the top is the simulation, using all the diffraction efficiency from our grading. The bottom is the actual experiment. And now this is the experiment where we've blocked one of the beams. So the first thing you can see is we have fewer electrons. No matter what the phase, relative phases, and the interferometer, we have fewer electrons hitting the detector, right? So we've blocked about half of them. So this is using a 50-50 beam splitter, roughly. So we have fewer electrons, but you can see where I put the red lines, the experimental condition. If that is our dark port, then you can see that those counts are now non-zero. Okay, so if I show a profile of this, here's the normal output that you'd expect. from our dartboard. We park right here, so we should be getting no counts. And here there's a small but measurable rise when we do block one of the beams, and that is this new thing that not been reported yet in the electron microscopes. If we have just a bar graph and counting this, so for every electron that goes in, they're all going in here. We have some dark counts at that pixel location. And if we just add those two, that's our total number. Now this is our beam in the interaction plane. So now we've apertured off our probe beam, and we see our dark port counts increase. Now, if we calculate the efficiency, it was only 14%. So the IFM efficiency was 14%, but that's still maybe of interest for ultimate goal here. But our probability for an error was still at 8%. So if we got a click in our dartboard, we might erroneously determine that there was an atom there. Okay. So now for the second iteration, we did two improvements. So we went to weak measurements. We purposely used a diffraction grating with a weak diffraction efficiency. So now our probe beam here is very faded. You can hardly see it. I think it was about 6% of the intensity in the bright beam. And then we used a single electron sensitive detector. And the other one, it was not single electron sensitive. We just had to integrate for a long time. So it was a stretch to call it single electron interaction reagents. Okay, so what does the output look like here? Well, again, we're going to scan these gratings back and forth, introduce the path length difference, and then we'll see that when we introduce block our probe beam, our total counts go down again. But now, in some locations, we get an increase in counts in the dartboard. I think what's more impressive is if we show just a raw image of our detectors. So this is a pixel array detector. We're just taking an image of the output of our interferometer here with single electron sensitivity. So with the sample removed, no shutter, there is our dartboard. We find the particular alignments of this interferometer. We've aligned everything correctly. Everything in the green box we've defined to be dartboard. Our blue box is just background. So what if we're scattering electrons? What if there's some detector noise? Let's look at that. And so now I show these in blown up here on the right. So you can see that there's some, it's showing up okay. Yeah, so you can see that there's some clicks in our dartboard, even when there's no signal in there. So that's a source of error. But now when we block the electrons, we see a sharp increase in the number of electrons hitting the detector. Now here we purposely spread out the electrons so we can capture these individual events rather than have them all hit a particular area. So you can see that there's individual little radiuses in there. Those are all related measurements. And there's no corresponding increase in counts in our reference area. Those are interaction-free measurements for electrons. Now we could image it this way, or we could express it this way. We look at the electron counts in the dartboard as a function of whether the shutter was inserted or not. And you can see a measurable increase even with the spread in our signal. Okay. Now, if we calculate what the efficiency here is, it was almost 31%. So again, assuming that whenever we got a bright or click, we would rerun the experiment, we would expose the sample for longer, then we could get an efficiency of 31%. Our probability of error corresponding to those dartboard counts, even when there's no shutter in, was pretty high. And so you can imagine having to take two measurements. If you got a click in your dartboard, maybe you want to wait for another one before you move on to the next area. Okay, so where are we now? Well, we want to see, can we, in principle, use this to form an image? And would it reduce the dose measurably. So this is a simulation. So we're simulated strange molecule. 80 from Minnesota. So this is for choice and a small app for a small molecule here. Now, one thing that I've slid under the rug is molecules are not opaque. They're very much phase objects. So keep that in mind. Here we're assuming an opaque object. What we're going to do is scan our interferometer in a raster scan over this area, such that a probe is passing through this object, our weak probe. So here we assume that our probe is about 5% of what the reference probe is, reference path. So here I'm using a very weak probe here. We're going to scan it across the sample, and we're going to allow ourselves five interactions before we declare a damaging event. So the damaging events are in red, and if we get a dark port click, an IFM click, then we call it blue. We say, there's an opaque object in the way. Okay, so I think this should probably be presented first. This is without any loss in our interferometer. So assuming that all electrons emitted from the source go to the detector or hit the sample. So this is less realistic on here. This is the more realistic one where we allow for the fact that our grating beam splitters are scattering electrons. They're also diffracting into other orders that we're not using. So there's quite a bit of loss in our system. In fact, about half of the electrons hitting the sample or entering the interferometer are being used. And that's a major source for our lack of efficiency here. Okay, for 15 electrons per position, that doesn't mean 15 electrons went through that pixel, that area of the sample. It means that roughly 5% of 15 went through that sample. So there's not many measurable ones. And still, you can dig out that there's some kind of object here. So now let's go with 30 electrons per sample. So we can imagine if only 1 or 2 electrons on average are actually interacting with each pixel, or if they were present, are interacting with it. And now we can start to make out the outlines. Now, 60 electrons per position. If you think about 5 electrons per pixel, and there's roughly 5% of our electrons. So 5% of 60 is actually hitting an opaque sample. That's when we're starting to see some damage. However, if we look at our IFM counts, there's more blue than red. So that means that we're reducing dose. You can imagine only using the red to form an image, whereas with IFM, we're imaging it much faster. And of course, if we oversaturate, then of course we're going to do damage. So at least according to this cartoon simulation, you could imagine imaging objects more efficiently. So bottom line, how's this happening? Well, in conventional cryo-EM, your phase contrast is very, very low. And so you have to expose for a long time, or you have to expose very minimally at an extremely noisy image. In fact, these are terrible signal noise ratios for an imaging system. But you want to image it before you damage it. And so that's why they're trying to take tens of thousands of images of identical particles to reconstruct the phase. With IFM, you have the same signal noise ratio. So you can use the same imaging mode, but now you've got this new special way to measure. As soon as you get a click in your dark port, that is a very high signal noise ratio detection of the damaging event. So as soon as you get that, you know there's something there. You can stop. You can move on to the next pixel. That's the idea. Okay. Well, we're starting to image things, so you can imagine scanning these probes across the sample. So here's a latex sphere, and that's a phase object as well as an opaque object. So here's an experiment. So this is an image of the latex sphere. So a very, very small one, 50 nanometers thick. There's phase introduced to the electron as it enters the material. So the mean interpotential is acting as an index of refraction, just shifting the phase of the electrons. And that's what we're sensitive to here. However, it's also scattering electrons. So this PAD signal detects scattered electrons. Those are the bombs, the scattering bits. Okay. Now, if we tune our quartz, so we're looking at a maximum, then you can see some phase contrast as we scan across. So there's no contrast as we're scanning through free space, but now we'll start to introduce it as we're going through, and this matches with what you expect from a sphere, the projected potential of a sphere. Now, if we tune to the minimum, now this is the dark or the interaction-free condition, where you should only detect an electron either if it's scattered from the sample or if it can't scatter from the sample, or if it's gotten a phase shift. So it's mixed phase and amplitude contrast here. Okay. So I'm not sure about this, but the talks, there was all this talk of embedded interferometers, these kind of island interferometers. So I kind of made this cartoon where this signal is your bomb. These are the electrons that blew up that area of the sample. But what if we model this sample as another interferometer? Except we can shift the locations of these mirrors. So what does this do? Well, these are tuned such that you get a transmission through. So we shifted these two mirrors symmetrically. So we get a nice output from our interferometer, just like we'd expect. Now, what we could do is we could shift both mirrors. So there's no relative phase shift in this interferometer, but there is a phase introduced in this path relative to this path. And so now we'll start to shift back and forth. We'll juggle back and forth between our bright and dark port and quadrature. So we're measuring that total global phase introduced by this object. So this is the phase contrast that we would expect for a perfect phase object. If we shift one of these mirrors, then there's now a relative phase introduced in this interferometer, and now we'll get start getting output into this other port, and those are like our inelastic scattered electrons. Those are literally electrons that scatter to some other detector, and so we can model this, toying with this idea of modeling this as if shifting in one mirror or both mirrors symmetrically. Okay. We can do other things like image electric fields around objects. So there's a charged object, we get some kind of phase contrast through the electric field. We can image magnetic fields, or more correctly, you can measure their magnetic vector potentials using a famous effect. Okay, so here's some topological defects in magnetization we're interested in. Now, there's a little bit of time. I'd like to talk about our inelastic interferometry. So these are interference phenomena using electrons that are lost energy to sample, which typically I would think of as collapsing our wave function. You shouldn't see anything. Okay, so to tell that story, first, these microscopes are pretty versatile. So it turns out that people have used these monochromatic electrons to map out all kinds of excitations in the material, including optical excitations. So here's an electron probe, not doing anything weird. We're scanning it over, let's say, a silver nanorod. And you can look at the scattered electrons just to form an image. But you can also have these electrons, the electrons transmitted through the object, go through a bending magnet. So they bend by 90 degrees. And the higher energy electrons have a larger radius. They'll still bend by 90 degrees, but they have a larger radius. You can use that to form an image of the spectrum of the electrons. And so if you park your detector, your selecting slit on, let's say, 0.55 EV energy loss, then you're able to map out optical excitations in these silver nanorods. So there's lots of work being done in this area. There's two references. Here's different optical modes supported in this small silver nanoware. Okay, so we can model this in different ways. But in a cartoon way, it's a classical electron going past this metal, and the Coulomb field acts as a single optical pulse. So these are fast electrons. If you're standing right here, you see no electric field, and then all of a sudden there's a growing electric field, and then it's gone. And that looks like a single optical pulse, so it excites in different modes. Now we can model this with a Hamiltonian, just one of our potential. And we can use Green's function formalism to actually calculate what is the likelihood of exciting a particular mode. So we break this object into a bunch of little dipoles, discrete dipoles, and we can look at the response of each of these dipoles, both to an electron and to each other, and use that to model the different plasma modes. Okay. So here's the setup. The question is, we've got an electron, let's say, passing on the right of this sphere. So this could be a little gold nanoparticle. As the electron passes, it shoves the electrons within the sphere over to the left. So it's just pushed a child on a swing as it went past. So it's repelled. Okay? And then as it goes, that child is going to start oscillating back. You've got the electrons in the gold nanoparticles are going to be oscillating back and forth. That's your plasma mode. And it looks like this, where they catch it in one cycle. And we can model that, so we can model the energy lost by the electron. So the energy is conserved, we just gain some to this plasma mode, which will eventually decay into a photon. And we can map out how much energy did the electrons lose. We get these characteristic peaks to tell you something about the permittivity of the gold and the size and whatnot. Okay, so if the electron passed on the left, it would excite the same mode, but it would push the electrons to the right. And so you've pushed the kid on the swing, you've pushed him from the front instead of back. The question is, what if you have a superposition of those? So what if the electron is in a superposition of the paths on left and right? What happens? Any guesses?
Newton's second law. Sum of the forces is equal to 0.
Yeah. So if you were to do this classically, you're running past a kid, and let's say your superposed brother, the other version of you is also passing on the other side of the kid. You both push the kid, and the kid doesn't swing. And so maybe we're able to suppress this excitation. So that's one reasonable prediction. Or consider the quantum thing. This is the environment, and it's decoherent the system. It's collapsed the wave function. That's another. Or maybe it's somehow in a superposition of both of those.
Yeah, but why not entangled?
Yeah, which turns out to be the answer. Okay. So here's what we did. So we have the probe here on the left of these nanoparticles. We pass it actually on both sides, left and the right. And then we're going to use our grating to recouple the two paths. So not just look at the interference fringes, but actually get them into a discrete output, and then run that through our spectrometer. And then we're going to image the interference fringes and see if we get high visibility interference fringes. Okay. So here's the model using the discrete dipole model. So one thing we want to press on is there's one particle. Right? We're going to have one particle, but we're going to scan our two probes past it. So when you normally image in a scanning CEM, you have an image, let's say this particle, and you scan the probe. So it's like involving a delta function with whatever you're looking at. But here we've got two delta functions, and so we see an image, a superposed image. And now if we energy filter the output of that interferometer, then we can see at these different optical modes this excitation. Okay. Now, one complicating factor is there's also let's say a natural log of one over R potential from the fact that this nanoparticle is stuck to a substrate. And that's actually useful because it introduces a background phase. So we can instead of tuning the relative phase between these two paths, we can use this background asymmetry phase to do it for us. Okay, here's what it looks like. Okay, so that middle image here, this is the image that we expect when we just use one beam, or the image that we picked, that's an actual picture. For this picture, we're using the scattered electrons. So those are electrons that interact with the sample hard and they scattered. We use that to form the image. It's a dark field image. Here on the right, this is a bright field image. So we're going to use the electrons that pass through coherently the sample, and we're just going to integrate them. And we see a double image for a sample. Now here's the output of that interferometer. So we can see that there's a phase. There's an electrostatic phase that's introduced to one electron over another. We use that relative phase shift to form an image. Here, we tune our interferometer to the dark. So it's on a dark fringe, and we see that we can start to see counts in there. Again, if we're just introducing a relative phase. Now, in this row of images, we're only selecting electrons that lost energy. So these are electrons that interact with the sample, excited at the plasma, and that's a hard interaction, and yet they remained coherent. They still interfered. In fact, we can tune that phase, that relative phase, use that background phase to form an image. So this is the start of an interference pattern. See that both for the dark port and the bright port, we see them kind of tuning in quadrature. Now there might be some decoherence here. This is a reduced visibility of our dark port. But we also think that there's some interaction-free measurement signal in there, especially since when we pass the beam through the particle, there's some non-zero scattered interactions. Okay. Now the other thing that we see is some contrast reversal. So if we look from the condition where we look at compared to the electrons that did not lose energy to the sample, the electrons that did lose energy to the sample have somehow not been measured. So the question is how? There's a superposition state, and they've actually lost energy to a system, and yet the system has not measured which path the electron took. So how's that? Did the electrons pass on the left, or did they pass on the right? And the system can't answer and just say, I don't know, but I know an electron passed. The answer to this is that we've excited the same mode. So you can imagine that this plasma, this sloshing electron plasma back and forth this way, eventually it will decay and release a photon, but that photon is going to be linearly polarized in this direction. And the photon can say which polarization it's in and what energy it has, and that's it. This photon over here is also linearly polarized. So no matter what, you're going to get a linearly polarized photon coming out. And the only difference is that there's a pi phase difference between those. And you can't measure that with a single photon. So what we found is this contrast reversal between unscattered electrons and scattered electrons is a pi phase shift. And you can directly relate that pi phase shift to the fact that this is a dipole excitation. Okay. I won't spend too much longer. I will say this is the ultimate goal is having a bunch of atoms, and you can focus the beams down to literally angstrom-sized length scales, and then use these tricks. So if we can't use the interference fringes directly. If we don't use an interferometer at all, we just use a single grating as a beam splitter, and then we directly image the interference fringes. So we're allowed to do that because it's a microscope. We can actually blow up this pattern, so it's resolvable. And if we do this as a function of position, we can see some interesting things. So here's a gold nanoparticle suspended on an amorphous, very, very thin carbon substrate. So there's a gold nanoparticle. You can see these lattice merges. So we're actually looking at the atom atomic planes within the gold. And in the normal imaging mode, you can't see much else, which is the point. Usually, if you've got a microscope slide, you don't want to see the glass. Here, the glass is amorphous carbon. If we use this interferometric imaging technique, we get both atomic resolution on a high Z material, but now we can actually see our amorphous carbon, our very, very thin, weak phase object. It's a very dim purple here. Here's another image. If I do a line scan, you can see that we start to see signal outside the soul. That's due to this carbon. And in fact, if we only image the carbon with our interferometer, electron interferometer, we can see features in here. And there's actually some stringy features. Sometimes there's rings. So it's not actually amorphous. It's these carbon chains that are forming. There's some theory. Believe it or not, papers written on amorphous carbon. What is the structure of amorphous carbon? It's consistent with that. Okay. Well, we do some other work with magnetic imaging that I can talk about in a whole other talk. It's another side of the lab. We're routinely using our phase shift, our non-reduced phase shift. For now, I'll just summarize that if we can image these things, we can make this and either increase the contrast even 10% or reduce the dose required to get this image by 10%, then that's already a pretty measurable and useful feature. So I think that can be an unintended consequence of quantum bomb detection. We can maybe do a quantum virus detector. Okay, so with that, thank you for your attention. Especially want to thank Amy Turner and Cameron Johnson and Peter, who helped us with this, and of course, the funding agencies. Thank you.
Yeah, that's remarkably beautiful work. Congratulations. In the interaction-free measurement business, the problem still is that you have to hit the molecules half the time in order to do an image. Is there any way of improving on that? I mean, a multi-pass operation seems to be more or less out of the question, but maybe there's some other trick that.
I think it would actually be the trick is going to be in our simulation moose. I might have oversplit because there the moose is going to block the electrons. If there's an electron there, actually there, then it'll do some damage or it'll interact with that. Now, in the molecule, there's an electron there that can. I think about phase shift as sort of a temporary interaction. So it's a transfer of momentum that it's going to get back. Mm-hmm. So it's a shift in longitudinal momentum and then eventually get that back from the object. So I don't know if you can count phase contrast as an interaction or not. I think I would. But the fact is, the probability of doing damage is still there. So there are some other tricks. So you can use your scattered electrons. So there's detectors where you can look at the electrons scattered at some angle. So you can actually measure whether they hit your object or not. You can look at your normal phase contrast. You can even look at the X-rays that come out. So if there's an excitation that didn't necessarily damage the molecule, but you get some kind of photon excitation, you can detect that. You can look at your phase shift. And you can look at this IFM. So the advantage of using the scanning probe technique is it's a multimodal imaging technique. Mm-hmm. And if you do that with all single electron, single photon sensitive detectors, and I mean, you can push it sounds better. Yeah.
You mentioned that you can image electric and magnetic fields.
Yes.
How weak an electric or magnetic field can you image? Do you know?
So we can get to, let's say, we can measure tens of microradians of phase shift. It depends on how long we integrate. So it's like within the interferometer, you integrate longer, you can get a finer delta pi on there. And so it's really limited by that. I think practically speaking, about a tenth of a milliradian is about what the limit is right now. And then if you look at the projected potential, I have a slide on that. The full index of refraction for an electron beam is dictated both by the electric potential it's going through, but also the magnetic potential. Watch it go here. And I know that for most materials, the mean enter potential is about 10 volts. Depends on whether it's metal or not. And so we can measure about right now a limit of 10 nanometers through that 10 volt material. We'd like to push that down and, for example, see if we can image graphene.
Yeah, there's the reason I'm asking is you might be able to do something that Yakir has been talking about for a while, if you can measure sensitively enough field strength. So we should talk about why.
Yeah, that'd be great. I mean, these images here, let's see. The idea with these electrostatic images is that we can charge this little wire. It's one wire that we could charge it up and tune that and use that as a phase flag. If we just park off here, you can see the space is varying pretty slowly. So that's a difference in potential between the two beams. And so, I guess just by shifting our beams, we can introduce this without having an optical element in there. This does suggest a kind of far out interpretation. So we're looking at one wire in this case, or here we're imaging, let's say, a single nanoparticle in these images. And then I've often wondered, what if you were the electron? So you're the electron in the interferometer, what do you see? And of course, it still goes because in order to see or to measure something, you have to be more complex than a single electron. But imagine you got a molecular interferometer. I think you would see possibly a superposition of two particles. So from the electron's perspective, there's a superposition of these two plasmonic particles. If it propagates, that new electron propagates right between them, it could excite both, but anti-symmetrically. And then if you're back in the lab frame, that same process happens. In that case, when the electrons propagate symmetrically between these two superposed particles in the lab frame, the particle is symmetrically surrounded by those two electron beams. So it'd be interesting to pursue a whole formalism in that picture.
Yeah, I think I missed it, but when you talk the setup, so magnetic lens, what are those things exactly? Is that like a space with field gradient or some sort of magnetic?
Oh, yeah. So I'm measuring instead of glass, just to make the analogy. Let's see. Here's one. So this is actually just the lenses are pretty complex. They've got a magnetic field that kind of shape the field around a huge coil of copper. You're running tons of current on it. However, all of that stuff is to stimulate and get as close as possible to an idealized circular loop of current. And so like in your introductory physics E&M class, you have to figure out what's the magnetic dipole field from a current loop. That is the field in these lenses. Yeah, so it's completely clear. And it turns out that electrons propagating through that field off axis get focused towards the optical axis. Except they get over focused too far towards the off axis. So it's like a spherical inversion.
Okay, thank you.
Okay, thank you.